So in oscillations, we're talking about simple harmonic motion is the very basic thing we're talking about here. Very common motion. We've talked about the motion due to a spring. Today we're going to talk about motion due to a pendulum. Again, back and forth motion. And where we left off last time is we've gotten sort of this far. So we're talking about some different little aspects of simple harmonic motion. And what we've got is we've got the position, velocity, and acceleration functions. They're sinusoidal. And so we kind of have two different choices. If you make the position a cosine function, then velocity has to be sine, acceleration has to be cosine. Again, they're all derivatives of each other. So if you look at velocity, it's the first derivative of the position, which is a negative sine function, and acceleration is the second derivative of the cosine function. Now you can also start over here with a sine function, then you end up with a cosine here and a sine over there. Now these are a little bit limited. We'll talk about this in a second, but for our purposes, we're mostly going to use just these. Here's what all the different maximums turn out to be, and then our relationship between period, frequency, and angular frequency. Very important. Now, the phase constant problem. So I asked this mistakenly the other day. I thought I'd go through it. Now, first of all, just don't worry too much about this. We won't deal with this too much. But what they do is instead of using just a straight up cosine or sine, they use the cosine function with a phase angle. Now, with the cosine and the sine, you're limited to where you can start from. If you use the phase angle, you can start from any point that you want to. So to find the phase angle, what you do is you do this here. So you look at the initial point at the 0 time. Okay, so at time equals to 0, the amplitude or the position is amplitude divided by 2. So for your position, you plug in amplitude divided by 2, and over here you plug in times 0 for that. And if you do that and cancel out these little amplitudes over here, you get cosine, the phase angle is 1/2. Then you just go to your calculator. Now you got to make sure your calculator is in radians. Okay, so this is the one time where your calculator has to be in radians. So you do radians. When I did this, I got like plus or minus 1.047, which if you put this in terms of pi, you'll notice that pi divided by 3 is the same thing as 1.047. Okay, so in your book, they kind of write it out that way there in your solutions. Okay, but it's the same thing. And so then the question is, do I use the positive or negative? Because both of them, cosine of the positive or the negative, will give you the same answer of 1/2. So you got to look at your velocity. At this position right here, at time equals to 0, your velocity, the slope of your x versus t graph is a positive slope. So you want velocity to be positive. So if you, again, make it for time 0, and then set about, okay, which one is going to make this a positive number. You look here, you got negative omega times a, that's going to be a negative term. So sine times negative pi over 3 gives you a negative. Okay, so negative times a negative, that gives you a positive. So it has to be the negative pi over 3. So generally, in a case like this, you've got to look at both the position and the velocity. Now again, we won't deal with this very often, but I think it is good to see what this really means, because our cosine function is limited that you can't just basically start at any position. If you put the phase angle in there, you can make this function start at literally any position between a and negative a. All right, so now acceleration. So we got the spring on the mass, or I'm sorry, mass on the spring. If you pull it some distance a, that's the amplitude, that's the maximum distance you're going to pull it. So the maximum force that this spring feels, or the force at this particular moment, is k times the amplitude. So if I do F equals ma, the force will be k times a, and then the m, now remember our maximum acceleration is this, omega squared times the amplitude. So in this equation, if I cancel out the two a's, I get k equals m omega squared. If I solve for omega, I get omega equals the radical of k over m. So this says for any spring connected to a block, okay, spring constant k, mass m of the block, the angular frequency, which remember, the angular frequency is just the regular frequency times 2 pi, is equal to this here. It only depends on the spring constant and the mass. Now, we oftentimes like to also express the period, and so the period is 2 pi over the angular frequency, and so in this case, it's 2 pi radical of m over k. So we can do a lot of information. So this is what you actually needed for the first part of the pre-class quiz. Again, sorry about that. So here's an example. We dealt with this system a lot in the last pre-class quiz. So you got a mass object of 8 0.80 kilograms. It's bouncing back and forth on a spring. We give you a graph of x versus time. I want to know is what's the spring constant k? Give this a try. Okay, hopefully you got 2.0 Newton meters. So the way we do this is the first step is to find the angular frequency. So from the graph, you know the period is 4 seconds. So 2 pi divided by 4 seconds gives us 1.57 radians per second for the omega. So actually, beg your pardon, it should be radians per second over here for the units. Then, from our new equation, omega equals the radical of k over m, I can solve for the k as omega squared times m. So here omega is 1.57 radians per second, and the m is just the mass of the system over here. So basically, you got enough information here to solve for the k constant. Now here's a conceptual style question. So a mass is attached to a spring, so two identical masses and springs. In the first case, we shoot it out, push it a distance a. In the second case, we pull it out a distance 2a. I want to know is in the second case, okay, so let's say in the first case we put out distance a, the frequency is f. I want to say if I pull out a distance 2a, what's the frequency going to be in this case? Okay, give us a try. All right, so this is kind of a trick question. All right, from our equation for this, we only depend, the angular frequency only depends on the radical of k over m. So the only two things for some system that this depends on is the spring constant and the mass. So it does not depend on how far you pull it. It'll have the same frequency. So what happens is in the case where it's 2a, it'll be bouncing back and forth with a higher velocity at different points. Okay, it'll have a higher maximum velocity, but it'll have the same angular frequency. Now, energy conservation. So if we have a spring system where the only thing acting is the spring force, this is the elastic spring force, will conserve mechanical energy. And so here's our mechanical energy. K plus U is equal to 1/2 mv squared plus 1/2 kx squared. So let's look at the sort of extreme cases. At the maximum displacement, x is equal to the a, the amplitude, and v is 0. So I get the energy is 1/2 ka squared. At zero displacement, x is equal to 0, and you have the velocity maximum. So essentially, at maximum displacement, the energy is all over here. It's all potential energy. At zero displacement, it's all kinetic energy. And we can show that these are in fact equal. So Vmax, the equation for Vmax is omega times a. So if I do 1/2 m omega squared a squared, if I throw in the fact that omega squared, we're going to use this a lot in the next couple of lines, so omega squared equals k divided by m. If I plug that in over here for omega squared, the masses cancel, and you get the same value. So the energy is in fact the same at the maximum displacement and at zero displacement. And in fact, you can solve this more formally. So here's our equation, kinetic plus potential. And so we plug in our functions of time. So I'm just going to pick the one we've been using the most, the a cosine omega t for the position, and the negative omega a sine omega t for the velocity. These are squared. Okay, so if we do that and write it all out, we get this kind of complicated looking piece over here. Now again, the same idea. Okay, I'm going to plug in for omega squared, I'm going to plug in the value of k over m. Okay, when you do that, this mass will cancel, and you're left with 1/2 ka squared sine squared omega t plus 1/2 ka squared cosine omega t. And with this, what you can do is you can pull out the 1/2 ka squared part, and then this here, of course, sine squared plus cosine squared is just 1. You get again the same value. So this is the energy at any time is 1/2 ka squared. It does not depend on the time. So in class, a lot of times we'll do a vertical spring. And so I just wanted to talk real quickly about that. So over here in our graph, we've got sort of three cases. So here's the relaxed position of the spring. When you put the block on it, the block is going to pull it down to some new distance that we're calling d in this little picture. Okay, so if I look at my forces, that distance, okay, I'll call it d over here, okay, and in the equation I'll call it y naught, is going to be equal to mg divided by k. So here's the spring force, k times y naught minus mg equals 0, and we call that this distance d. And so what happens is if we make this our new 0 point, okay, what will happen is when the spring oscillates, like in this case C over here, it's going to oscillate about this new equilibrium position. Okay, we can show that here. So now, if I do my k force, so any displacement from there will be k y0 minus y. minus mg equals ma, what happens is if I plug that in, so here I distributed the k times the y naught and the y, so you get k, so k mg divided by k is just mg. This mg and this mg cancel, and I'm left with now just negative ky equals ma. And so basically, if you adjust the position of the spring to the new equilibrium position, okay, this is just simple harmonic motion, you can essentially just forget about the gravity. So the new equilibrium position will be this negative y naught. Of course, in our little picture here, we called that d, so it bounces around that position d. Now here's a picture for the pendulum. So here's our pendulum. The two forces of the pendulum are the tension going up at the angle theta and then mg. That's our free body diagram. So this mass is going to slide back and forth like a pendulum. And so what we do is you can write out the two forces of mg into their components, mg cosine theta, mg sine theta. And if I look at just the tangential, okay, part of this, mg sine theta. Now, for very small oscillations, sine of theta equals theta. So very, very small, tiny angle, sine of theta and theta are the same. If you want to check that out, you can, but make sure you use radians, otherwise it won't work, okay? It only works if you're in radians. Just because degrees are kind of a tricky thing to deal with. So here, I'm going to use our definition of theta as s over L. That's the definition of a radian. Okay, so here, this is the distance L here, and then this s would be the actual distance that you're moving here, the arc length. Okay, so if I do s divided by L, I can write it in a special form here. So we know that our spring force looks like k times x. Well, here it would be mg divided by L, and the distance s would be our x. So our k constant for a pendulum for very small oscillations is mg divided by L. We can then take this, okay, and plug it into our equation for simple harmonic motion. So the k constant is mg over L. If I plug in mg over L here, the m's cancel, I get g over L. If I try to just extend expression for the period, I get that it's 2 pi L over g. So you get these two expressions, but the important part is that the period and the frequency, okay, do not depend on the amplitude A or the mass, as long as, again, that angle is very, very tiny for small oscillations. And so we can ask ourselves a final question here. So on planet X, a ball on a massless rigid rod oscillates as a simple pendulum with a period of 2.0 s. If the pendulum is taken to the moon of planet X, where the free fall acceleration is half as big, the period will be what? Okay, so hopefully you got this answer here. So on planet X, so the period on planet X, which I just call sub e, so I'm assuming it's kind of like the Earth, but here's the period on Earth is 2 pi L over GE. Okay, on planet X's moon, this guy is the GE divided by 2. And so I divide by 2, which is the same thing as bringing the 2 upstairs over to here. Okay, so we get this expression here. And so now what we do is we divide the two guys by each other. And so this is the one that's off by a factor of 2. And you get rid of everything in here except for this radical 2. And so you get that basically on the moon of planet X, it's radical 2 times what it was on the planet X. And if you plug that in, you get 2.8 seconds. So finally, to end this chapter, we don't talk about this stuff too much, but they have this idea of damped oscillations. And damped oscillations basically means there's friction. So when there's friction, you've got essentially a combination with an exponential function with a sinusoidal function. And so if you actually watch a spring go back and forth, what happens is it'll start going back and forth, okay, really high like this, and then eventually it'll start going smaller and smaller as it loses energy. And so this thing is losing energy as it goes on. So it's a damped oscillator, and the function would look something kind of like this here. But the key is that basically instead of just going back and forth forever, it'll eventually go back and forth and stop. And then finally, the idea of driven oscillations. So every system of oscillator, okay, and we've talked about mostly springs and masses, has a special natural frequency. Okay, and how do we find that natural frequency? Well, the omega for a spring and a mass was equal to k over m. Okay, and the way that it works is if you have that special frequency, okay, the system is very very sensitive to this frequency. So this graph over here is basically the amplitude you can get on your system versus the frequency. And you'll see that it peaks at the natural frequency. So if you drive this oscillator with a natural frequency, okay, it's going to have a very high amplitude. If you drive it off the natural frequency, it won't be. An example they use in the textbook is they have somebody playing a special note for, say, a glass of a wine glass. Okay, and the wine glass is an oscillator, has a special frequency. If you hit the note at that special frequency, it'll really make the wine glass vibrate and eventually break. Another example is if you're pushing a kid on a swing set. Okay, the swing set and the kid have a certain natural frequency. If you hit them, okay, give them a little push exactly at that natural frequency, you can get them going really good. Whereas if you kind of hit them kind of haphazardly, not at that natural frequency, they won't have a very large amplitude. So that if you want to drive an oscillator, you've got to do it very close to that natural frequency. Okay, thank you.